Hello everyone. In this video, we will be discussing another topic from springs. That is springs under fluctuating loads, and along with that, the type of springs what we discussed previously, where we will be focusing on one type, that is leaf spring. So, what is the stresses and strains which is inducing on the leaf springs, and even equalized and the nipping of leaf springs. All those things we will be discussing in this video. So, before moving to that one, we have a very important topic, that is the design of springs against fluctuating loads. So, in many applications, the force acting on the spring is not constant but varies in magnitude with time. Example here, fluctuating load, when we speak about, we just go back to the I designed one where we have discussed different types of loads and even different types of stress cycles also we have discussed. So fluctuating load is something where the amplitudes will not be same. If you take any cycle, if you take any frequency cycle, if you take means maybe the upper amplitude and lower amplitude it may not be same. And if upper amplitude and lower amplitude is same means we call that as one cycle, where the second cycle amplitudes may not be same with the first cycle amplitudes. So such kind of loads will be calling as a fluctuating load. And moreover, this fluctuating loads we cannot say that it is limited only with the first quadrant, that is the positive quadrant, like only at second or third quadrant we cannot limit. Sometimes it can have a mean stress more, or it can have other kind of stresses, amplitude stresses less, on the variable stresses, like all those things can be different. So fluctuating load one more information is we cannot say that this fluctuating load axis it will exactly lie on the x-axis. We cannot say that it may be above the x-axis or it may be below the x-axis. And sometimes you can able to see, just now I said it is of a positive quadrant, need not be, like even negative quadrant also will be there. Similarly, like a third and fourth quadrant also will be there. So the valve springs of automotive engines are subject to the millions of stress cycles during its lifetime. So here the examples for the fluctuating load what I have chosen is the automotive engine valve springs. So on the other hand, if you see means the springs in the linkages and the mechanisms are subjected to comparatively less number of stress cycles. Okay, and here you should be very careful with the valve springs and the linkage springs, because valve springs are something where continuously it will go under the loads. It may be usually the storing of mechanical energy will be there. But if you see the linkages, particularly the springs what we used in the linkages, where the mechanisms are very comparatively it is very less, and also the stress cycles also whatever it is resulted in, that also is also very less. So these kind of stresses, I mean, if you see this, both the springs will be located on the engine only, like an automotive engine. Valve spring also will be there, and also like the linkages springs also will be there. So what happens? Just now we discussed, like the valve spring will be having more stresses compared to the linkages. So there will be a fluctuation in the stresses. So the springs subjected to the fluctuating stresses are designed on basis of two criteria, that is a design for infinite life and a design for finite life. I think whether you people remember or not, in SN diagram already we have studied about the shaft, like life, particularly for the shaft only we have discussed, because we have chosen an application where the repeated or the cyclic load which is going under. So a shaft is one such example where continuously it will going under a torsion that we discussed. So where based on the SN curve only we will be, and I think you remember, like if the number of cycle is at 1000, 10 power 3, or 10 power 4, 10 power 5, 10 power 6, 10 power 7. So from 10 power 3, from 10 power 7, if there is a constant increase, and after 10 power 7, if there is no like a drop, or if there is no increase, then such kind of thing we will be recommended for the infinite life. So in between 10 power 3 and 10 power 7, if there is a sudden fall means, then we will be recommending that for the finite life for so and so cycles, it may be 10 power 4 or 10 power 5. So the cycles which is coming less than the 1000, so it may be 900, 950 also, but usually we cannot recommend that kind of materials for whether for the infinite and for the finite life. So in case of the fluctuating, we are calling definitely these kind of materials should come under out of these two categories, that is the infinite life and the finite life. Now you can able to see like the graph what I'm talking about. We need not to discuss all the graphs of maybe for different types of stress cycles what we discussed, which is not required right now since we are focusing only on the fluctuating stresses. That fluctuating stress graph is sufficient. Here have a look on this particular graph. As I said, it is fluctuating. Fluctuating means in cycle it is not shown properly, but since only two cycles are shown here. But correctly speaking, if you see the third cycle or fourth cycle, means there will be some fluctuation. And here you can able to see. So the tau a indicates nothing but amplitude shear, and tau m is indicates the maximum like mean shear, and this is nothing but the maximum shear. So maximum shear usually will be calculated with from the what is that reference axis to the maximum amplitude peak point, and this graph is plotted versus time and stresses. And here the minimum shear is always zero, because this graphical reference line, it is not lying on like the timeline. So whenever if this is the case, means always the minimum shear stress will be equal to zero. So now let me write down directly the formula for the fluctuating stresses, that is 1 by fluctuating stresses, which is equal to tau m minus tau v divided by tau v, that is the mean stress divided by the variable stress divided by variable stress, plus 2 times of variable shear divided by like effective shear. So this all about the design of springs under fluctuating load. So we need to consider the SN curve very importantly, and later we need to remember the finite life and infinite life as the limits or the criteria for deciding the material of the springs for the fluctuating curve. Then moving to the next type, that is the design of the leaf spring. So we have discussed many type of springs, like even like a pull type, a push type, compression type, all those things we have discussed. But among that, in our syllabus, where the design of leaf spring is given, you can able to see the varieties of the leaf springs. So when you look at these images, I think one could easily can remember where you have seen this. Particularly for the heavy load applications, if you can take automobiles, trucks, buses, cars, and even some like high duty vehicles, anything you can take, means you can able to see this. And usually where this leaf spring is provide like is present, means in between the two wheels, the transmission shaft will be there. So to reduce the vibration, because whenever the torsion is transmitted from the driver to the follower, the like the lengthy a transmission shaft will be there, a huge vibration will be there as a result of a like a torsion, that is we can call it as a fluctuating torsion. So to reduce or to keep the like transmitting shaft in control, usually this leaf spring is recommended. And even we'll be discussing a couple of the problems in leaf springs, and all these leaf springs for the different applications is mentioned here. So now along with the leaf springs, we need to discuss the characteristics of the equalized and the nipping of the leaf springs. So sometimes this is all leaf spring is also called as the semi-elliptical spring, as it takes the form of a slender arc-shaped length of spring steel of rectangle cross-section, and also the center of the arc provides the location for the axle, while the tie holes are provided at either end for attaching to the vehicle body, and it supports the chassis weight, controls chassis roll more efficiently, high rear movement center and wide spring base, controls rear end warm-up, and controls axle damping, controls braking forces, and regulates wheelbase length. And the leaf springs, if you see in the cantilever beam type of leaves, I have chosen one example, like for the nipping and equalized thing, I have chosen a cantilever beam where the case 1 and case 2 is given, and based on the basic equation for the bending stress and deflection, the maximum stress and the tip deflection is derived here. So for the case 1 and the case 2, you can able to see for the uniform width and non-uniform width, where the maximum stress is 6 FL by BH square and the maximum deflection is 4 FL cube by EBH cube. And for the non-uniform width, it is maximum is 6 FL by BH square, but the maximum deflection is 6 FL cube by EBH cube. So here the differences between uniform and non-uniform is the deflection only, we can able to see that. And moreover, the bending stress and the shear stress curves we can able to see in the bending moment diagram. Thank you. And even the other cases also we can able to see it here, that is sigma max, and for the uniform width cases along with the bending moment diagram we can able to see the formulas. Thank you.